Section 13.1 is transformations of functions, and we're going to talk about 3 different types of transformations. So reflections about the x and y axes, vertical and horizontal shifts, and compressions and stretches. So the first 2 types are called rigid transformations. So these 2 are called rigid transformations because the shape of the graph doesn't change. But then you can probably tell by the name of the third one that if you're compressing and stretching, you're changing the shape of the graph. So once you have all those functions from section 10.4, and so you have your library of functions that you're really familiar with, then we need to add the idea of transformations, and this will multiply by many times the number of graphs that you're able to just sketch quickly, and you'll find this a really useful skill. So the transformations you need to know is vertical shifts up and down, horizontal shifts right and left, vertical compression, and vertical stretching, and then horizontal compression and horizontal stretching. Then we have reflection about the x-axis and reflection about the y-axis. And you need to pay close attention to the order in which these transformations are applied, because it can make a big difference in the result. So we'll talk some about how you know what the order is. So first let's look at reflections about the x and y axis. And if we multiply by a negative number after the function has applied, this will cause every y coordinate to be the opposite what it was, and the graph will reflect about the x-axis. So we're first talking about reflections about the x-axis. So if I have a function, r of x is the opposite of 2 square root of x, well, the square root of x function looks something like that, and if you multiply it by a negative number, then it reflects about the x-axis because every positive y value now becomes a negative number. So then we have reflecting about the y-axis, and if you multiply the argument, what's inside the function, before the function happens, you multiply by a negative number, that causes reflection about the y-axis. So it's harder to find good examples of this, but let me go ahead and use the square root example again. If I have the square root of x and then I apply the negative before doing the square root, then hopefully you can see that you need to put negative numbers into the function now, and so it has the effect of reflecting the graph about the y-axis. Okay, so then we have vertical and horizontal shifts. If you add a number after the function has happened, the graph of f gets shifted up that many units. And if you subtract a number, then that has the effect of shifting the graph down that much. So the example of x squared, here's the basic x squared graph, and then if after the squaring of the x you add 2, that doesn't change the shape of the graph, it just moves every y value up 2 from where it was. And then if we have the square root of x, and then we do minus 4, that's going to have the effect of subtracting 1, 2, 3, 4 from each y value and not changing the shape of the graph. So this is the transformed graph. This is the parent graph of square root of x. So let me just take a minute to go back and talk about identifying the parent graph. So the parent graph is the square root of x. And here the parent graph, square root of x. In this example, the parent graph is x squared. And here the parent graph is, again, square root of x. So I think it's really helpful to identify the parent graph. Okay, so vertical shifts are pretty intuitive. They make sense to most people. Horizontal shifts a little less so. So if the argument of the function is replaced by x minus some positive number, it shifts the graph right h units. And if you think about this, we've already been dealing with this idea when we did the circles. And we had, if in the circle equation it had x plus x minus 2, we said, well, the center then had an x coordinate of 2. Well, that had the effect of moving the graph to the right 2 from 0, 0, where it was originally. So subtracting before the function is applied shifts the graph to the right. Then adding, if you add something before you do the function, it's going to shift the graph to the left. So you need to figure out some way of explaining this to yourself so it makes sense. To me, it's counterintuitive, and so I've just learned it as it's backwards of how it seems like it should go to me. So here, let's identify the parent graph in this example. X cubed. So x cubed, hopefully you're getting to where you can just draw a quick x cubed. And then if I have x plus 5 inside the parentheses before the cubing is happening, that's going to move the graph 5 to the left without changing its shape. So again, we're still here in the land of rigid transformations where the shape doesn't change. Okay, then this one might be a little hard to recognize the parent graph, but just think of things being added and subtracted and multiplied as visual clutter, and try and zero in on, oh, the base graph, the parent graph that I'm starting from is 1 over x. So hopefully that's another one in your bag of tricks. This is a hyperbola. This is the only hyperbola that's a function. We'll learn about hyperbolas in the conic sections part of the class, but then they won't be functions. So this is the only one that's a function. So let's see, y equals 1 over x. So let's think about what happens as x gets large. So as x gets large, y is heading to 0, because if you divide by a bigger and bigger number, the result gets smaller and smaller. So in fact, the x-axis is a horizontal asymptote. And then as x heads to 0 from the right, and this is a symbolic notation that you'll learn in calculus, as you head towards 0 from the right, y is getting larger and larger because you're dividing by a smaller and smaller number. So the arm of the hyperbola looks like a curve in quadrant 1, and then its mirror image in quadrant 3. So this is a symmetric graph. It's symmetric about the origin. And then I have a minus 3 being applied before I'm doing the reciprocal function. So that's going to shift the entire graph 3 units to the right without changing its shape. Okay, so then we are going to work on combining transformations, and here's where the order becomes important. Look at the x first and focus in on the x, and then think about order of operations. So the first thing that's happening is 4 is being subtracted from the x before the absolute value function is being applied. So if I subtract 4, that shifts right 4 units. And that's the first transformation. Then the second transformation is we shift up 3 units because that adding 3 happens after the absolute value function has been applied. So let's make a note that the parent graph here is y equals the absolute value of x. So you would know what graph is it that you are applying transformations to. So in this next example, the parent graph is x squared. And focus in on the x and say the first thing that's happening to x is 3 is being added. So that's going to shift left 3 units. And then after the squaring happens, there's a -7. So that's going to shift the graph down 7 units. Okay, so that's our reflections and vertical and horizontal shifts. So then we come to compressing and stretching. So we're first going to talk about vertical compressions and stretches. So again, this focuses on whether the thing is happening before or after the function. So previously we had negatives told us about reflections. Adding and subtracting caused right, left, up, down shifts without changing the shape. And now we're going to be multiplying by something. And if you multiply by a number between 0 and 1, the new graph is vertically compressed. So I would love it if you would think through this and say what's happening is after you have found the y value that you used to plot, you're multiplying it by a number like a half, and so every y value is half as much as it was. So these come up a lot more in trigonometry, or if you have a graph like this and you say, oh, I'm going to have a vertical compression, the graph zeros don't move, but its mountains are half as high and its valleys are only half as deep. So then if you multiply by some number bigger than 1, then you're going to get vertically stretched version of the graph. So let's look at these two cases. So if I multiply the function by a number that's bigger than 1 after I apply the function, it would look like this first example where we have the parent graph of y equals x squared. So let me first draw the y equals x squared. And then multiplying every y value by 2 has the effect of a vertical stretch of the graph. Every y value is twice as large as it was, but notice that 0, 0 doesn't move at all. Okay, so then if you multiply the function by a number between 0 and 1 after the function has been applied, that would look like this example. And let's do this one in red. And so each y value is a third as large as it was. So it has the effect of vertically smushing the graph, or compressing is the formal word, where somebody sat on it and squashed it down. Then we also have horizontal stretch and compress. And again, this is where multiplication is happening, but it's happening before or after the function. So let's see, this one is before. So vertical stretch compress is multiply after the function. And I'm going to pause here and start again with another video so that it's not too long.